today I would like to talk about the pesticide removal in stormwater biofilters. So Megan has already presented that there are some pesticides that existing in stormwater. So we would like to see how our stormwater biofilters remove the pesticides. So moving on to the outline. So today I would like to mainly talk about the removal of pesticide in biofilters, and through some specific experiments. We did 3 major experiments, and I will be introducing this. And also I would like to share the knowledge we have about the surrogate for pesticide removal in stormwater biofilters. And also at last I want to briefly talk about the modeling of pesticide removal in stormwater biofilters. So moving on to the next slide, for my interest, we only tested a few pesticides, atrazine, simazine, and promethazine, which are commonly found in stormwater. And the atrazine, simazine, and promethazine, they are quite similar in terms of their chemical structures and also their physical chemical properties and half-lives. And the glyphosate is a bit different from other 3 pesticides, and it has less mobility, and it has lower biodegradation rate. It has lower half-lives. And we expect that in stormwater biofilters, the removal of this pesticide will be mainly through the absorption during the rainfall event, and also there will be slow biodegradation over the dry periods between the stormwater events. So next slide, it shows 3 different major experiments we did. The first is the in-situ challenge test we conducted on our Monash car park biofilter. And also back in the laboratory, we did a laboratory colony experiment to understand the breakthrough curves of those pesticides using the soils collected from the car park biofilter. And also we developed the in-situ tool, in-situ columns, to study the pesticide removal in the field system. So on slide 5, so this is our Monash car park biofilter, and before we did the experiment, we came up with a few challenging conditions that was analyzed using music. So first of all, about the dry period, so we came up with 2 conditions. One is pretty wet conditions, so like we only have a dry period of 10 hours. And the second dry period is 21 days, which is quite challenging dry period as we found in Melbourne. And also in terms of the volumes, we dose 3 pore volumes for the consecutive events, which means that 2 events with very short dry period, and 4 pore volumes for a single event. And the inflow concentration, we were also targeting very high challenging concentrations. Challenging concentrations. So we used 2 milligram per liter for glyphosate and 60 microgram per liter for simazine, atrazine, and promethazine. So according to these challenging conditions, we designed 3 tests over around a month time. So test 1 was done under normal conditions with very challenging volume, and test 2 was mimicking very challenging concentration with only 12 hours of dry period. And test 3 was done after 21 days of test 2, in which we also dosed a very high volume of inflow. So test 3 is basically a very challenging dry condition. So we studied 2 different types of biofilters, and one is the sand biofilter with a submerged zone, and another one is a loamy sand biofilter without any submerged zone. So let's have a look at the results. So this table basically gives the outflow EMC concentrations of the 3 tests for those 2 biofilters, and we can see that the biofilters are very good at removing glyphosate concentrations. The reduction could be up to more than 90%. However, in terms of the triazines, the atrazine, simazine, and the promethazine, the removal by stormwater biofilters wasn't very good, and its outflow EMS concentrations were almost achieving the inflow concentration. So we still need to optimize these biofilters further to enhance the removal of these triazines. And this is the next slide, slide 7. This shows the intra-event variability of the concentration change over the 3 tests. So this is, I'm giving an example of simazine concentration. So as you can see, in between test 1 and the test 2, there's very short dry period. So from the beginning of the test 1 to end of the test 2, the simazine concentration were increasing all the time without any decline in the dry periods. However, after a very long dry period between test 2 and test 3, so we observed a decline of outflow concentration change. So basically means like the starting concentration of simazine in test 3 is lower than the finishing concentration of simazine in test 2. So that indicates that the slow biodegradation of simazine is happening during this dry period. And also comparing those 2 different biofilters, although they are very different in their configurations, but we can roughly tell that the low methane biofilter, which is the blue dots, and it has a better removal performance in removing the simazine, as the low methane has a higher organic matter content than the sand and filter medium. So this is the in situ experiment. The next slide is shows how we did the laboratory column experiment. So basically, we designed the laboratory columns exactly the same. I mean, in terms of the soil profile as to the field challenge condition, and the inflow volume was we dosed these columns with the pollutant with the pesticides, and then flush it with a certain volume. So for this one, because the glyphosate has a much higher absorption potential than the triazines, so we dose the more volumes and also use the more volumes to flush the column. And the inflow concentrations were close to the field challenge experiment. And here I want to see like this, the soils collected from the field were sterilized. So in here, in this laboratory column experiment, we were only studying the adsorption process. And the adsorption process will be the main process during the wet period. So moving on to the next slide, I'm showing some breakthrough curves of these 4 different types of pesticides. So for the atrazine and the simazine, because they are very similar in terms of their mobility and their half-life and their physical chemical properties. So you can see the curves are very similar. And after 4 pore volumes of dosing, the outflow concentration of simazine and atrazine almost reach the inflow concentration. However, as for prometrine and glyphosate, because they have a bit higher adsorption potential, especially for glyphosate, the log KLC value is much higher than the other 3. So we can see that, for example, the glyphosate, even after 15 pore volumes of dosing, the outflow concentration still reached only 0.3 of inflow concentration. So the biofilters will have a bigger potential for removing the glyphosate. And from these curves, we can also see that the biofilters wouldn't be very good at removing the atrazine and the simazine. So further work should be done to optimize the media and to optimize the systems for to enhance this removal. And in terms of glyphosate, although it's currently showing that the biofilters are doing good job for removing glyphosate, but we still need to look at the long-term accumulation of this glyphosate in the stormwater biofilters. So next slide, slide 10. So we we developed some in-situ columns. So instead of doing some field challenge experiment, we want to develop some in-situ columns that will enable us to do the experiment easier and with low cost. So we were trying to develop a in-situ columns for our study. So basically, the concept was to insert these in-situ columns in the field side and collect the water from the bottom of the columns with collection pipes. And so next slide, slide 11, shows the design of this in-situ column and some photos. So you can see from the photo figure 2, so this is shows that there are some holes underneath the column, and we have a chamber sealed those holes on figure 3, and there's also a collection pipe. And during the experiment, we were pumping the outflow water from the collection pipe. However, the pumping rate was carefully calibrated in order to avoid the acceleration of filtration. So next slide, slide 12, shows the results we've got. So the black points shows the in-situ challenge test, as I introduced in the beginning. So that's the results from in-situ challenge test, and then the colored points shows the results from the in-situ column experiment. So as we can see that the in-situ columns, they are good at mimicking the trend of pesticide simulation concentration over the 3 experiments. And however, there are some differences. The in-situ columns always produce slightly lower outflow concentrations than the in-situ challenge test. However, we observed that there are quite different climate conditions in between those 2 different experiments. So the in-situ column experiment was conducted in winter, while the field challenge test was conducted in summer. And then they also have different antecedent fortnight rainfall and participation between participation between the test 3 and the test 4 for the in-situ column experiment. But we can still argue that as long as we are using these in-situ columns under very strict conditions and under strict challenge conditions, these columns will help us to get some reasonable results we need. So moving on to the next part, we want to talk about some potential surrogate for this pesticide removal in biofilters. So during the in-situ challenge experiment, as well as the laboratory column experiment, we also tested a range of potential surrogates that could be used for the pesticide removal. So in slide 14, this shows the linear regression between the surrogate and the herbicide remover. So you can see, let's focus on the phosphorus, total phosphorus and the total dissolved phosphorus. We can see a very strong linear correlation between the reduction of phosphorus species between and the pesticide we tested. And also we found out that the UVA, which is ultraviolet absorbance, is also highly related to the reduction of atrazine simulation perimetry. So those 2 will be some potential surrogate used for pesticide removal in stormwater biofilters. And we think that because of the similar processes occurring between the potential surrogate and also the pesticides, that the reason that make them significantly chlorated, especially for the adsorption process during the rainfall event. And back in the laboratory, we were targeting in slide, I'm on slide 15. So this shows the linear correlation between the glyphosate reduction and the total phosphorus reduction. So you can see by comparing the field experiment against the laboratory experiment, we observed very similar results. And this basically tells us that this significant correlation between those potential surrogate and the pesticide was due to the similar processes that was accounted for the removal of the pesticide. So the next part on slide 16, I would like to briefly introduce the stormwater biofiltration treatment model for modeling pesticide removal in biofilter. So this was done by one of our colleagues, Anya Ranovich, and she developed this model. And this model has two major components. The first is the hydrodynamic component and the pollutant transport module. So if you are interested in this model, you can refer to her paper for more details. And for the hydrodynamic model, we have a dispersion coefficient as a parameter. And the pollutant transport model is a process-based model. We model the absorption process using the chemical non-equilibrium two-side adsorption model with the instantaneous fraction of absorption, kinetic parameters such as soil partitioning coefficient, and also first-order kinetic absorption rate. And the biodegradation rate was could also be accounted using the first-order decay. And I applied this model for my laboratory colony experiment, basically in slide 17. So I'm using this model to calibrate the parameters using my laboratory breakthrough curve experiment. And the calibrated parameters were then used to predict the in-situ challenge test under the in-situ challenge test experiment. And the next slides, I'm showing some good results of the model application. So for parametering and the graph set, and the dot points is the measured data from the in-situ challenge test, while the red lines shows the prediction data based on the laboratory column calibrated parameters from the laboratory colony experiment. And you can see that this model can produce reasonable good results to predict the field performance. However, the uncertainties, you can see the predictive uncertainties, they grew over the three tests, especially at the beginning of the challenge test 3, which was conducted after a very long dry period. So this long dry period introduces a lot of complex processes like evapotranspiration and that biodegradation process that was not very well captured during the laboratory experiment. So come to the conclusion. So we found out that the stormwater biofilters are good at removing the glyphosate remover. However, it's not very efficient for removing the atrazine and the simazine. And also the in-situ columns we developed could be a good tool to test the pollutant removal in the field biofilters. And also we found out the phosphorus species are a good surrogate for the pesticides, and also UVA are good surrogate for atrazine, simazine, and prometrin. And the stormwater biofiltration treatment model that we developed could provide some good prediction, could be a good tool to predict the field performance of the biofilters for removing pesticide. And also, personally, I think we need to do some feature work for example, to optimize our filter media to enhance the simazine and atrazine removal, as the current biofilter media is not able to remove very good, to provide a good removal of atrazine and simazine. And also the long-term performance should be investigated for the pesticides. And also further work could focus on some surrogate reliability under different conditions. So that's it from me. If you are interested in more details of this experiment, you can refer to these papers. Thank you.
Thank you, Kefeng. That was a wonderful data set, and I'm really pleased to see the acronym for your model is MPIRE. So you probably didn't realize that, but now I can take credit, right? Yeah. So I guess we want to go to some questions. I'm sure there are some questions out there. But I kind of wanted to lead off, just ask you a little bit about the Empire model. Um, so you showed the predictions of the model compared to the data for some contaminant results, some breakthrough curves. How does the model perform from a flow perspective? So presumably you start looking at the flow predictions, and then once you've got that nailed down, go to the breakthrough curves.
Yeah. So the prediction results I'm showing here is just the application of my experiment, and this model was uh, on was originally calibrated against the field experiment in terms of the flow and also the pollutant. And the flow, because the flow was very well predicted actually with very high model efficiency. And this is especially for the case because I introduced two different kind of biofilters. And for the biofilter, we send filter medium and submerged zone that was extremely well captured in terms of the flow. However, for another biofilter, because that other biofilter was not very well designed, so and we had some problems with the modeling of the flow.
Great, thank you. Are there any other questions for the audience?
I had a couple questions about what you think would be, sort of looking forward, good ways to modify biofilters for removal of trizones, given that atrazine is prevalent in groundwater everywhere.
Yeah, yeah. So the first thing on my head will be use some different medium that, for example, biochars and some zeolite, if that could be helpful to enhance the pesticide removal. And another thing will be because we haven't looked into we only tested a couple of systems for the pesticide removal, and we would like to see if some specific plants will be helpful to remove the pesticides. So that could be another direction that we can go to enhance this. Thank you.
Thank you. Yeah.